All right, welcome back, everyone. This is just a quick mic check. Can you just let me know if you can hear me okay, and you can hear me okay, and you can see my. All right, perfect. Thank you. So we're going to pick up from where we left off yesterday, and that is to say, we want to talk about the equivalence class labelings that we were doing for a variety of NIM game states. So what we said yesterday was that if you are at a particular game in G and it happens to have some label, let's say the label. Okay, let's actually not ascribe a label to G because that's what we're trying to figure out. So let's say that in the game tree, the game G has a bunch of child states. So let's say that these are all the games that you can reach by making a single move in G. And let's say that these states in turn have labels associated with them. We said, suppose those labels are N1, N2 up to NK. This is just to say that the game GI is equivalent to the game of NIM with a single heap, which has NI sticks in it. This is what we are claiming implicitly with an induction hypothesis, if you like. And we want to say that, well, if this is the case, then G itself is equivalent to the NIM game with a single heap, which has these many sticks. These many is the mix of all the NIs. That's the minimum excludant. It's the smallest number, the smallest natural number. So I'm saying natural number, but it also includes zero. So it's the smallest number in N union zero, which does not feature in the set N1 through NK. And we've discussed some intuition for why we want to look at only excluded numbers, why G is not equivalent to any of its children. And we've actually proven yesterday that among all the excluded numbers, the smallest one is the correct label to use. And the way we did that was by showing that when you combine this game and whatever this number turns out to be, let's say that it turns out to be N. And I think what we did yesterday was to show that G plus star N is P, which is necessary and sufficient condition for establishing that those two games are equivalent. So I will spare you a recap of the proof because I think we did walk through it, unless somebody would explicitly want to go over it again. And then if that is the case, please let me know in the chat. But what I want to talk about today is the idea that you can figure out the label associated with a NIM game, which is a combination of these individual games. By using a very natural binary operation or a natural operation on the binary representation of these numbers. Okay. Unfortunately, my screen's frozen. I just need 30 seconds to resolve this, hopefully. Right. So we want to say that this number here is equal to the ZOR of the individual NIs. And so that's the notation for ZOR. And just in case that's an operation that you haven't seen before, well, that's an operation that basically picks up the parity of the number of ones in each column of the binary representation of these numbers. So let's try to work through this with an example, which makes it easier. So suppose we have what, n1 is 3, n2 is 6, and n3 is 8. Let's say we're working with 3 numbers or 3 NIM files. The heaps have 3, 6, and 8 sticks respectively. So let me write out these numbers in binary. So 3 would just be 1 and 1. What about 6? That's going to be 1, 1, 0. Right, that's 4 plus 2. And 8 is going to be 1, 0, 0, 0. And what is the ZOR of these 3 numbers? The way we calculate that is to basically go column wise, and under each column you record the parity of the number of ones that we see. So if we see an odd number of ones, then we have a 1, and if we have an even number of ones, then we have a 0. So that's going to be 1, 1, 0, 1, if I'm not mistaken. And as a number, I mean, interpreted as a number in decimal, this is going to work out to 13. And the claim is that that's the label that you associate with the game that consists of 3 heaps with 3, 6, and 8 sticks in them. Okay. So that, but we could also work through more examples of like taking ZOR if you like. But let me okay, now have a warning from Zoom about an unstable connection. Hopefully, as far as I can tell, my screen share is still on. Yeah, okay. So, right. So at least we know what we are claiming here. We're claiming that the way these numbers associated with NIM games combine is by taking the ZOR of the corresponding variations of these numbers. And again, incidentally, if you haven't encountered ZOR before, it's also called, I think, the exclusive OR, which is to say that if you're combining a 1 and a 0, that's 1. But if you're combining a 1, 1 or a 0, 0, then that's a 0. And so when you extend that to a set of numbers, it just ends up being a reflection of the parity, the parity of the number of ones. Yeah, so that's an operation that's just useful to remember. Now when do we okay, so when do we end up with a P situation, which is to say when So if this is going to actually be 0, according to our understanding of max, for example, so that's going to a p position. That means that, well, that means that every child must be n. Okay, all right, yeah. I noticed in the chat that my voice is apparently breaking. I do have notifications from Zoom saying that my connection is unstable, so it's probably gotten something to do with the network. I can try to switch out to a different network unless if you can confirm that everything that I said for the last 30 seconds is kind of okay. All right, okay, thanks. Okay, let me just carry on and hope that it stabilizes. But let me know again in the chat if you're unable to hear me, and maybe I'll try to either restart Zoom or change the Wi-Fi network that I'm on. Okay. So I'm just trying to build up some intuition here for what might be going on with the XOR. So let's try to understand what happens when we are claiming that we have a 0 game. In terms of the XOR, right, we are saying, so on the left-hand side, this notation is the game sum notation. So this is just to say that we are working with k piles of nim at once, and the ith pile has ni stakes on it. And if the combined game has a label of 0, well, that means that it's a p state. And remember that you have a p state if all your children are n, which means that every possible game that you from the one that you are at is winning for the current player. That's the player who starts with that modified game, right? And on the other hand, we also were claiming that this is the XOR of the NIs. And so let's see if we can build some intuition for that. It means that if you focus on, so you write down your NIs in binary. They don't necessarily have to have the same number of digits as we saw earlier. But if the XOR is 0, then what it does mean is that when I look at the outcome, this is 0. That means that the number of ones here must be even. Okay. And let's assume that, well, we're implicitly going to be appealing to induction, because whenever you're working with a game tree, then that's just a very natural tool to have handy. So what do I mean when I say induction? I mean that this sum sensibly works for any smaller game. And once again, you can think of the size of a game as the total number of stakes involved in it. So currently we have summation ni many stakes. And a smaller game would have just strictly fewer stakes in them. So once you make a move in this game, what are you essentially doing? You're grabbing some stakes from one of these piles, right? So you're moving to a game that would typically look like exactly the current game, except that one of the piles has strictly fewer stakes than before. Now, everything else is the same, right? So this is what any child of this combined meta game is going to look like. Any child will have this configuration. Now, if you go back and look at the bit representation of the children, then what's happened? If we think about the NI that has changed, that's going to correspond to one of these rows getting updated. In some way, updated to a different number, a number that we know is smaller than the current one. But it also does mean that there is some column, so everything else is the same, but there is some column where one of the bits is flipped. There might be multiple columns where the bit has flipped. The bits have flipped. Sorry, grammar, rest in peace. But anyway, so when you change ni to ni prime, right? What happens to the number in binary? So, for example, you could say that I'm going to take 6 and I'm going to make it 5, right? What would that entail? Well, that's going to be 1, 0, 1 or something like that. So notice that this bit flipped, and so did this one. But notice that all the other rows are exactly the same, but because you don't get to touch any of the other heaps, right? And we know that at least one bit flips, because if none of the bits flipped, then the heap in which you were playing is also unchanged, which means that you didn't actually make a move at all. So that's not the case. So we do know that the heap that you're playing on had at least one of its bits being flipped. And that's actually all we need to make our argument, because let's focus on the earliest column where you see a bit flipping. Okay, so I'm going to start off from the last column and work my way backwards. And I stop moving as long as I see, I stop moving as soon as I see a bit being flipped in the heap where the move was made. Okay, and notice that if this was a 0 before, then it must be a 1 now, mainly because whichever way the flip went, it's going to disturb the parity of the number of ones. And I hope that is clear. So if you flipped from a 0 to a 1, then you increased the number of ones. And if you flipped from a 1 to a 0, you decreased the number of ones. And you had an even number of ones to begin with in this column. So let's say you had some b1s, and that both b minus 1 and b plus 1 are odd numbers, right? So this 0 flips out to being a 1 in the XOR sum. Okay, all right, the internet unstable again, but this is a natural place for me to take a breather and ask if this is making sense. So what I'm trying to say here is that if the XOR sum of all the numbers that we are working with is 0, then the moment you make a move in this game, you end up with a collection of numbers whose XOR sum is non-zero. Does that claim make sense? It's probably enough for me to say that Ni prime is different from Ni, but we know that Ni prime is the result of a move being made in the ith heap. Excuse me. So we're really only interested in such tuples, starting from these ones here. So starting from here, this is the state or the configuration that you can go to by making one move. And my claim is that if you started off with a bunch of numbers whose XOR sum was 0, then no matter what state you go to, those states are going to have a XOR sum that is non-zero. And again, the reason for that is that the move essentially flips at least one bit in one of the rows of the sum, and it doesn't touch anything else. So the column in which the bit flip happened, and indeed every column in which the bit flip happened, the result changed from 0 to 1 because the parity was disturbed. With 1 bit flip, you also flip the parity. It doesn't matter if it was previously a 0 that flipped to a 1, or if it was previously a 1 that flipped out to a 0. In both cases, the parity is disturbed. Is this comment fair? Okay, perfect. Thank you. So where do we want to go from here? So this is effectively an argument in support of the fact that your 0 labels, when you're taking a XOR, if the XOR happens to be a 0, then that's actually correct, because remember that our labeling was such that a game being equivalent to star n is winning, or is an n state, if and only if n is greater than 0. Right? Because that's, we said when we were doing the equivalence classes that the 0 label goes to all the p states, and then we built it up from there. So everything that's not labeled 0 is actually an n state, just by the definition of how we did the equivalence classes. So, or how we did the labeling. So we know that that's the situation here. And so if we have a 0 label, that means that we are claiming, in particular, among other things possibly, that if the XOR sum is 0, we are claiming that this guy here is a p state. But the way game trees work is that if you want it to be a p state, then all your children must be n. But we have seen that if we ascribe labels by XORing, and we inductively assume that that's an accurate thing to do on any smaller game, then we know that all the children have a XOR sum that is non-zero. And therefore, because of this claim here, we know that all of these children must be n states. So we are appealing to the induction hypothesis to say that, well, all the children that we can go to look like this, their XOR sum is non-zero, and that the XOR sum is an accurate labeling of that state. That's where we're using the induction hypothesis. And then we know by the nature of our labeling that if the label is non-zero, then it's an n state. So all the children that we have moved to are n's. They're all winning for the current player, which means that the current game that we are at, where the XOR sum was 0, must actually be a p, because it only has n children, children of the form n. And that means that, well, we have a p, so the labeling of 0 as prescribed or suggested by the XOR sum is indeed correct. Okay, so when the XOR sum is 0, we know that we are making sense. It's adding up, no pun intended. Things work out. What happens if the XOR sum is non-zero? And in this case, I don't know if I have enough time to convince you about the label of the equivalence class, but let me at least convey the intuition to say that if the sum is non-zero, then it's not a p state. Okay, let me prove that tinier claim, and then I think we'll, from there, showing that the labeling itself is also accurate, that it reflects the mix as we wanted it to, is not particularly difficult. So let's think about what I want to show here. I want to say that now I'm in the situation where the XOR sum of the ni's is not 0, right? So I'm giving it some label, which is, let's define this to be, let's define the XOR sum to be n, and we are in the case where n is non-zero, right? So in particular, n is strictly greater than 0 because all of our values are non-negative. And what I want to say here is, at the very least, this is an N state. Because if it wasn't, then it's a P state, and then we are in trouble, because then we shouldn't have given it a non-zero label. But what does it mean that it's an N state? It means that there exists a move, there exists some I such that if I go to the file, if I go to the game where we have made a move in the ith file, then, and it's an appropriate move, then that game is losing for the current player. That game is a P. So I want to say that there's basically one P child. And so any child has this form. So notice that previously our burden of proof was that we had to show that every child was an N. So we made a comment about no matter which heap is disturbed and no matter how it is disturbed, there's going to be a flip. And that flip takes us to something that is non-zero. Whereas here, we only have to show that there is some way of morphing one of the numbers so that the XOR sum becomes zero, under the assumption that the top level XOR sum that we started out with was non-zero. So we are going to use the non-zero-ness of the XOR sum of the NIs to be able to find this NI prime. And remember, just finding one is enough. Okay. So maybe let's try to do this by example. We dealt with the 368 a moment ago. So let's recall that that looked like this, and it did have a non-zero XOR sum. So now I want to make a move in one of these. I don't know which one, such that once the move is made, the new XOR sum is going to be zero. Now, I also cannot change this number arbitrarily. It has to be a number that is smaller than the current one. And I'm sure that if you spend some time in trial and error, you'll find something that works. But the idea of doing the example is to hopefully come up with a way of doing it that generalizes to an arbitrary collection of heaps. So we shouldn't be relying on any specific facet of this example. The example is really just an excuse. So what do I want? I want all the outcomes to become zero, which means, for example, if I wanted this one to become a zero, my only hope is to change this one to a zero. There's no other way that I can force that kind of outcome. So that already forces that I want to play in this file here. So let's write down the other two and keep them as it is. And now this is really just a subtraction problem in the sense that we know that we want this outcome. And we just need to reverse engineer the correct set of bits to position here so that we get the outcome that we wanted. So every time I had a 1 in the old sum, what I want to do is take the file that I'm playing in and flip the bit there, because again, that bit flip will disturb the parity. And now it disturbs the parity in the opposite way, meaning that the older parity was odd. And now flipping the bit, whether it is a 0 to a 1 or a 1 to a 0, will change the parity of the number of ones from odd to even this time, right? So in particular, I have ones in the first, second, and the last positions here. So I'm going to flip those bits out. 0, 1, 0, 1. That's what I get. So this is actually a 5. And recall that this was an 8. So our strategy here will be to move in the pile that has 8 sticks and reduce that number to 5. And if we do that, then we have a new we have a new game where the XOR sum is in fact 0. And we have just argued before that we know is a p-state. We're convinced that this is a p-state. That's something that we've worked out already. So what did we do in this example? We said, well, okay, basically look at the leftmost one in the sum. Right. So you're looking at the XOR outcome of the NIs. It's a bit string. And we know that the bit string is a non-zero bit string. Otherwise, we would not be having this conversation right now. So surely there's a one somewhere. There are probably multiple ones, but there's at least one of them. And so let me take the most significant one. So everything is 0 until the BI shows up. And this is a 1. And then the rest of it is something. I don't really care. Because the BI is a 1, there must be at least one heap where the number of stakes in that heap interpreted in binary has a 1 in the ith position. Because if this column was all zeros, then BI would not be a 1, right? So there is some heap where the ith bit is a 1 for sure. In our case, this happened to be the last heap. And in this example, there was a unique heap. This may not be the case. In general, we could have had 3 heaps or 5 heaps. There could be any odd number of heaps that have this property that BI is 1. Now, it doesn't matter. Pick any of them. It's just important that the leftmost, so basically, yes. I mean, I did say leftmost. I think I just want to make sure that we are affecting all the ones that are there in the outcome. So I want to make sure that I get all of them. So in any case, let's pick one heap where the BI is guaranteed to be a 1. And what we do in this heap is that we flip this 1 to a 0 so that this BI becomes a 1. And we continue flipping for all the outcome locations that are 1. You continue making those flips, right? And now you're left with a number that is guaranteed to be smaller, because this is where I think it's important that you've taken a leftmost bit and made the flip 1 to 0, as opposed to, for example, a 0 to 1, right? So if I flipped, for instance, if I go from 1001 to 1101, well, that's a bit flip, but it's making the number bigger overall, which would not work. So the leftmost flip that we made was a 1 to 0 flip. And that's crucial in ensuring that you're going to a smaller game. Otherwise, the move itself may not be valid. Okay. But you do that, and then everything else you flip, as per taste. Basically, you know that the outcome is supposed to be 0. So you flip all those locations which were a 1 in the old sum, so that the final outcome is 0, just like we saw in the example, right? So that means that whenever you have a non-zero XOR sum, then there is indeed a move that you can make that takes you to a 0 XOR sum, right? So we know that the XOR sum is at least making sense to the extent that it's giving you a valid state label. But that's, of course, a coarse sort of a claim to make. So let me leave this as food for thought in terms of, why does the XOR sum also give you actually the right number? Why does it position this game in the correct equivalence class? That's something that's just nice to mull over a little bit before we take it up when we meet tomorrow. And if we have some time tomorrow after discussing this, we will also get into a little bit of examples of other variants of NIM and other impartial games before moving on to games on graphs, which I've been promising for a while. And hopefully that's just around the corner. Okay, so Preeti, sorry, I only just saw your question about how do we ensure that it is smaller. So notice that in the outcome zeros, in the outcome XOR sum, I basically walk up this sum till I find the very first one, right? And I only flip starting from there in some heap which has a 1, and everything else before this is unchanged, and this flip was a 1 to a 0. Future flips may be 0 to 1 flips or 1 to 0 flips. But because the leftmost flip that we made was a reductionist one, the number does not become bigger. So that's a very valid question. And I noticed you did say that you followed, perhaps because we also discussed it as you asked the question. So anyway, I thought it was worth repeating because it is an important aspect of this whole argument. So thanks for helping me emphasize it. And I think this is a good place to perhaps call it a day so that we are more or less on time. And we'll continue this conversation tomorrow, talk a little more about XOR sums and their properties and NIM variance. That's the plan. Thanks so much.